we are still trying to visualize and understand neural networks, in particular convolutions, and try to visualize them, understand them. Last session, we had some discussions about the results of this paper, and I think it's a good idea to address that. So what are we saying? There was this trend in deep learning that neural networks generalize really good from training to testing. But people were skeptical, and the reason was that these neural networks are heavily parameterized. It means that they are intuitively able to overfit the data, the training data, and there is no reason for them to generalize to unobserved observations. But then people came around and they tried to justify it. They said maybe neural networks generalize well because there is something special about their architecture. Maybe there is something special about convolutions that's preventing them from overfitting. And this paper came around and said, okay, let's assume you're right. Let's assume that the model architecture in itself is a sufficient regularizer. So it's going to prevent overfitting. Let's assume that's correct. And now let's create a counterexample to that. And the counterexample is this: fitting random labels and random observations should be really hard because this is just noise that you are trying to fit, and fitting a noise is really difficult. And if there is something special about neural networks architecture, they shouldn't be able to fit noise. But what happened is that they trained this network on random labels and even random pixels. Yes, it is harder to fit them. It's going to take longer, but eventually you're going to overfit noise. What does it mean? It means that there is nothing special about a neural network architecture preventing it from overfitting. So that couldn't be an explanation. So there is nothing special about a neural network architecture, or it isn't sufficient. It isn't a sufficient regularizer. There was another explanation, which was saying that neural networks generalize because we regularize them, either explicitly or implicitly. But then the same thing happens when you do regularization. You're still able to overfit noise. You're able to overfit noise. It means that even explicit regularization isn't sufficient for controlling the generalization error. It means that they can still overfit, even in the presence of random crops and weight decay and these sorts of explicit regularizations. There is an implicit regularization. That one seems to be helping more. And that's when you are having a validation data set and you take a look at your error on the validation data. And whenever it starts to go up, you stop your algorithm, you stop the training. As soon as you see that your error on the validation data is going up for a couple rounds of training, you're going to stop it and say, let's stop here. The network is overfitting. That one seems to be helping the most. But then the paper took it even further. It said, yes, that's a counterexample. This is another counterexample. But actually, neural networks are able to overfit. And that's proof. I can give you a neural network with 2 layers deep, with a ReLU activation, and given enough capacity, it's going to overfit. And that's proof that neural networks can overfit, indeed. So that's an impressive paper. Any questions about this before I move on to the next one? So the next paper is going to be the last paper that we cover when it comes to visualization and understanding. But I want to make sure that everything is clear before I move on. Okay, perfect.